Hello, my name is Kevin Craig. I have created 12 modules covering electronics and measurement for mechatronics. Modern engineering practice requires that engineers model, analyze, and predict before they measure. Mechatronics. The diagram you see I created in 1995 as a professor at Rensselaer Polytechnic Institute. It is now used around the world to represent the field known as mechatronics. Mechatronics is multidisciplinary systems engineering. It is the synergistic integration of physical systems, electronics, controls, and computers through the design process from the very start of the design process. These modules present the fundamentals of electronics and measurement for mechatronics. This is the first in the series of modules. And in this module, we cover DC circuit analysis. The topics we will cover are general model structure for electrical systems, voltage, current, resistance, and power, DC and AC circuits, complex numbers, Kirchhoff's current and voltage rules, loop current analysis and node voltage analysis, ideal voltage and current divider, Thevenin and Norton equivalent circuits, impedance matching, electrical sources, real and ideal voltage and current sources and meters, circuit loading, and impedances of electrical elements. The diagram you see shows the general model structure for electrical systems, and it applies only to linear electrical systems. A linear dynamic system has three attributes: capacitance C, resistance R, inductance L. The variables we use to describe electrical dynamic systems are voltage E, magnetic flux phi, current I, and charge Q. The capacitor relates the voltage E to the charge Q through its constitutive equation. The resistance R relates voltage E to current I through Ohm's law. The inductance element relates magnetic flux phi to current I through Ampere's law. Voltage and magnetic flux are related to each other either through the integral or through the derivative according to Faraday's law. Charge and current are related to each other either through the derivative or the integral by the definition of current as being the rate of flow of charge in an electrical system. The electrical equations of motion and the constitutive equations for the electrical elements in an electrical system will contain integrals and derivatives. However, we will not be performing integration or differentiation, as MATLAB and Simulink will perform the numerical differentiation and integration for us, and we will be operating in the domain of algebra and trigonometry. However, it is essential that you understand the physical meaning of the derivative and integral. And I've chosen a situation that is familiar to you from the field of dynamics, and that's the rectilinear or straight line motion of a rigid body. And I'm looking at the relationship between position, velocity, and velocity and acceleration. I know that the derivative of position with respect to time is velocity, and the derivative of velocity with respect to time is acceleration. What did these mean physically? If I look at the position versus time curve, the slope of the curve at some time t1 is equal to the value of the velocity at that time t1. And the slope of the velocity versus time curve at time t1 is equal to the value of the acceleration at time t1. If I look at the areas under these curves and start with the acceleration versus time curve, I see that the area under the acceleration versus time curve between times t1 and t2 is equal to the change in velocity between those times t1 and t2, or v2 minus v1. Similarly, the area under the velocity versus time curve between times t1 and t2 is equal to the change in position of that rigid body between times t1 and t2, or x2 minus x1. Shown here is an example of what we just discussed. A person is in a building 20 feet above the ground. He throws a ball vertically upwards with an initial velocity of 10 meters per second, plus 10 meters per second because we assume the positive direction is up. I'd like to know the motion of the ball from the time it leaves the person's hand until it hits the ground sometime later. I'll need to integrate acceleration and then velocity to get position of the ball as a function of time. I can do that using MATLAB and Simulink and numerically integrate both acceleration and velocity. The initial acceleration of the ball is minus 9.81 meters per second squared, the acceleration due to gravity. It's minus because it points down. The motion is rectilinear motion, straight line motion. The ball goes straight up and then comes straight down. And I want to know what that motion is as a function of time. So I integrate acceleration to get velocity with an initial condition that the velocity is plus 10 meters per second at time t equals 0. In MATLAB Simulink, the symbol for integration is 1 over s. The output of this block is then the velocity as a function of time, which I can then plot. If I integrate velocity, again, 1 over s, with an initial height of plus 20 meters, I get position. And so I can then plot both velocity and position as you see below. Here is my position versus time curve. We see that the position starts at 20 meters, gets to a maximum height of 25 meters at 1 second, and then lands 3.28 seconds later. The velocity starts at time t equals 0 with a velocity of 10 meters per second. At 1 second, when it reaches its maximum height, the velocity should be 0, and it is. And the velocity when it hits the ground, 3.28 seconds later, is minus 22.17 meters per second. So I see that the slope of the position versus time curve is equal to the velocity at that time instant. So the slope at time t equals 0 of the position versus time curve is equal to 10, and that is the initial velocity at time t equals 0. At time t equal 1, the slope is 0, as the tangent line is horizontal, and the velocity at t equal 1 is 0. At t equal 3.28 seconds, the slope is equal to minus 22.17, which is the value of the velocity at time 3.28 seconds. Similarly, I can look at the area under the velocity versus time curve, and I do it for a portion of the curve from t equals 0 to t equal 1, and I find this area to be plus 5. That should be equal to the change in position of the ball from t equals 0 to t equal 1. And indeed, at t equals 0, the ball's height is 20. At t equal 1, the ball's height is 25. So the change in height is plus 5. Let's talk about voltage, current, resistance, and power. All basic electronic circuits consist of three separate, related electrical quantities: voltage, symbols are V or E; current, symbol is I; and impedance, the symbol is Z, and impedance is defined as voltage over current. We begin with the resistor, symbol R, and its impedance, Z sub R, which is the resistance, R, according to Ohm's law. Voltage is electrical potential energy stored in the form of an electrical charge. Voltage is the effort that pushes electrons through a conductor. The greater the voltage, the greater is its ability to move the electrons through a given circuit. As energy can do work, this potential energy is the work required in joules to move electrons in the form of an electrical current around a circuit from one point or node to another. 1 volt is the electrical effort required to have an electrical current of 1 ampere through a resistance of 1 ohm. The difference in voltage between any two junctions, called nodes, in a circuit is known as the potential difference, or voltage drop. A constant voltage source is called a DC voltage, direct current. A voltage that varies periodically with time is called an AC voltage, alternating current. Voltage can exist across a circuit without current, but current cannot exist without voltage. Here are the voltage symbols: single cell, multiple cells or a battery, DC voltage source, and AC voltage source. Electrical current is the movement or flow of electrical charge, Q, and is measured in amperes, A. An ampere is the number of electrons or charge in coulombs passing a certain point in the circuit in 1 second. It is the continuous and uniform flow of electrons, which are the negative particles of an atom, around a circuit that are being moved by the voltage source. Electrons flow from the negative terminal to the positive terminal of the supply. However, for ease of circuit understanding, conventional current flow assumes that the current flows from the positive to the negative terminal. Resistance is the capacity of a material to resist or prevent the flow of current, that is, the flow of electric charge within a circuit. The circuit element which does this is called the resistor, symbol R. Here we see the symbol for a fixed value resistor and the symbol for a variable resistor. A resistor's value is determined by the relationship of the current through it to the voltage across it, which determines whether the circuit element is classified as a conductor, semiconductor, or insulator. Resistance can be linear or nonlinear in nature, but never negative. Linear resistance, called ideal, obeys Ohm's law. Voltage equals current times resistance. As the voltage across the resistor is linearly proportional to the current through it, it's called an ohmic device. Nonlinear resistance does not obey Ohm's law, but has a voltage drop across it that is proportional to some power of the current, and that is called a non-ohmic device. Pure resistance, that is, only resistance with no parasitic capacitance or inductance, is not affected by frequency. Resistance is always positive, never negative. A resistor cannot store energy, only dissipate energy as heat. Power in a resistance is always positive, regardless of voltage polarity and current direction. Power, defined as voltage times current, with Ohm's law can be expressed as I squared R or E squared divided by R. The reciprocal of resistance is called conductance, symbol G, with the unit Siemen, S, and represents the ability of a conductor or device to conduct electricity. Here we see a voltage source connected to a resistor. The resistor is assumed to be pure and ideal. That is, ideal means linear. Pure means only has the attribute for which it is named, resistance. There is no parasitic inductance or parasitic capacitance. We connect a voltmeter across the resistor as voltage is an across variable. We connect an ammeter in the circuit so the current passes through the ammeter, because current is a through variable. By Ohm's law, resistance is voltage over current. And we plot that here, current on the y-axis, voltage on the x-axis, and we see we get a straight line, according to Ohm's law. Impedance for a resistor is simply the value of the resistance. The impedance of a resistor, Z sub R, is equal to the voltage across the resistor divided by the current through the resistor. Let us define more formally what electrical impedance is. A variable that flows through an element is impeded by the element. Electrical impedance with symbol Z is a generalization of the simple voltage over current relation called resistance, R, for resistors, designated as Z with a subscript R. It can be applied to capacitors, inductors, and to entire circuits. It assumes the linear behavior of the device. It is defined as the function relating voltage to current. Impedance is most useful in characterizing the dynamic behavior of components and systems. Electrical power in a circuit is the rate of doing work, or the rate at which energy is absorbed, produced, or transferred. Energy equals power times time. A source of energy will produce or deliver power while the connected load absorbs it. Light bulbs and heaters, for example, absorb electrical power and convert it into either heat or light, or both. The higher their value or rating in watts, the more electrical power they are likely to consume. Power is the product of voltage multiplied by the current, with the unit of measurement being the watt. 1 watt equals 1 joule per second. A convenient conversion is 1 horsepower equals 746 watts. By using Ohm's law and substituting for the values of voltage, current, and resistance, the formulas for electrical power are power equals voltage times current, which equals current squared times resistance, which equals voltage squared divided by resistance. Electrical components are given a power rating in watts that indicates the maximum rate at which the component converts the electrical power into other forms of energy, such as heat, light, or motion. For example, a 1/4 watt resistor or a 100-watt light bulb. Electrical devices convert one form of power into another. An electrical motor converts electrical energy into mechanical energy. An electrical generator converts mechanical energy into electrical energy. A light bulb converts electrical energy into both light and heat. This is a supplement covering the mathematics of energy E and power P. It is not essential for our discussion at this time, but we will need to refer to it later on. Here we see that voltage is defined as work per unit charge. A volt is a joule per coulomb. Current is the time rate of change of charge. Power is the time rate of change of work. Power can also be expressed as the time rate of change of energy, and energy then is the integral of power with respect to time. Power is voltage times current, and we see here that voltage is work per unit charge, current is charge per unit time. Multiplying these two together, we get power as work per unit time. So a watt is equal to work per unit charge, joule per coulomb, times charge per unit time, coulomb per second, or joule per second, which is equal to a volt times an amp. We can get two expressions for energy depending on what form of Ohm's law we substitute into the integral. Here we see the change in energy between 2 points is equal to 1 over the resistance times the integral of the voltage squared with respect to time. An alternate expression for the change in energy is the resistance times the integral of the current squared with respect to time. And this is the energy dissipated by a resistor, as a resistor cannot store energy, only dissipate energy. This is a table that shows Ohm's law formulas. It relates resistance, current, voltage, and power once known values are given. It's a useful table that is derived from our basic formulas. We often use prefixes for our units. For resistors, the most commonly used prefixes are mega ohm, kilo ohm, or simply the ohm. For inductors, the most often used prefix is millihenry. And for capacitors, the most often used prefixes are microfarad and nanofarad. DC and AC circuits. AC and DC current. Current that flows in a single direction is called direct current, or DC. And current that alternates back and forth through the circuit is known as alternating current, or AC. Whether AC or DC, current only flows through a circuit when a voltage source is connected to it, with its flow being limited by both the resistance or impedance of the circuit and the voltage source. Here we see a constant voltage source, a pure and ideal resistance, R sub L. The current flowing through the resistor is related to the voltage across the resistor by Ohm's law. Here we see a plot of current versus time, and Ohm's law tells us that the current flowing through the resistor is equal to the voltage divided by the resistance. The graph shows that this current appears instantaneously. That is not possible physically, but for a pure resistor, which has no parasitic inductance or capacitance, this is what the response would be. But in the real world, a resistor always has some parasitic capacitance or inductance, and so the response for the current as a function of time, once the voltage is applied to the resistor, is not instantaneous, but very fast. Keep this in mind as we deal with real components versus pure and ideal components. Let's consider 4 commonly used quantities. The first is the watt hour. The watt hour is the amount of electrical energy consumed by a circuit over time. If the electrical power consumed or generated is measured in kilowatts and the time is measured in hours, then the unit of electrical energy is kilowatt hours. A 100-watt light bulb will consume 2,400 watt hours, or 2.4 kilowatt hours in a day. The second quantity is the decibel, with the symbol dB. The decibel is a unit used to represent gain, either in voltage, current, or power. It is a logarithmic unit commonly used to represent the ratio of output to input. The dB ratio of an output voltage, E out, to an input voltage, E in, is expressed as 20 times the log to the base 10 of the ratio of E out to E in. The third quantity is the phase angle, phi. The phase angle is the difference in degrees or radians, where 180 degrees is equal to pi radians, between a voltage or current waveform and a voltage or current waveform having the same period, capital T, where T is equal to 1 over f, where f, the frequency, is measured in cycles per second or hertz. The phase angle is a time shift given by theta in degrees times the period t in seconds divided by 360 degrees. And the time shift can have a leading plus or lagging minus value. The phase angle of a waveform is measured in degrees or radians. The fourth quantity is the angular frequency, omega. A complete revolution or cycle is 360 degrees, or 2 pi radians. Frequency f is revolutions or cycles per second, or hertz. Frequency omega is radians per second and is equal to 2 pi f. Here we see 4 diagrams of periodic waveforms: a sine wave, a complex wave, a triangular wave, and a square wave. 3 of its characteristics are period t, the length of time in seconds that the waveform takes to repeat itself from start to finish. Frequency f is the number of times the waveform repeats itself within 1 second. The unit is cycles per second, or hertz. Frequency is the reciprocal of the period, t. Lastly, amplitude A is the magnitude or intensity of the signal waveform measured in volts or amps. For a pure sinusoidal waveform, the average or mean value is always equal to 0.637 times the maximum value of the waveform, in this case, Vmax. Here we see a non-sinusoidal waveform, and we'll focus on the positive half cycle of the waveform. We see Vmax, the peak value is identified. The average value here is shown. And if we sample the positive half cycle at 10 instants in time, n is equal to 10, the value of the voltages at each instant in time is called the mid-ordinate values, the mid-ordinates. The average value in the positive half cycle is determined by summing the mid-ordinate values, in this case there are 10, and dividing by the number of sampled values, in this case n is equal to 10. There is a value of the voltage defined as the root mean square that's calculated by first squaring the values of the mid-ordinates, hence the word square, summing them and dividing by the number of values that were squared. So in this case, n is still 10, so the word mean. And then we take the square root, hence the word root. Voltage, root mean square. Now, what does this root mean square voltage mean? Well, the equivalent value for an alternating current system that provides the same amount of electrical power to a load as a DC equivalent circuit is called the root mean squared value. For the sine wave, the root mean squared value is 0.707 of Vmax. And we will see why this is so. So we note that the average, the root mean squared, and peak values of a sine wave are all different. So here we see again the positive half of the sine wave just blown up, and we see the mid-ordinate values. They're equally spaced. So if this is half of the sine wave period, this is 180 degrees. And the RMS value then, in words, is given by the sum of the squares of the mid-ordinate voltages divided by the number of mid-ordinates. So we see here in symbol form, it's the values of the mid-ordinates squared, then summed, and then divided by the number of mid-ordinate values, and then the square root of that expression, of that number. And that gives us the root mean squared value of the voltage. Continuing on with our discussion, I show here a sine wave in the solid blue line. The peak value is V peak. The sine wave can be expressed as V peak sine omega t. Omega is the frequency of the sine wave in radians per second. Radians per second times time in seconds gives me radians, so omega t is theta. If I want to know what the average power is delivered to a resistive load over one cycle, the mathematics tells me to integrate from 0 to the end of the period the instantaneous power v squared over r, integrate that with respect to time, and divide by the period to get the average power. If I focus on the power in this half cycle, I now can switch from omega t to theta. I integrate between 0 and pi, which is the half cycle, of Vp squared sine squared of theta divided by r, my, again, instantaneous power, and I divide by pi, which is the period of this half cycle. If I integrate that, the mathematics will show that this is equal to 1 over r times v peak squared divided by 2. Now, if I then ask the question, what is the value of the DC voltage that will give me the same power delivered to my resistive load as the AC voltage sine wave, what I see is that that voltage is the RMS value from my sine wave. And I calculate the RMS voltage from this expression to be the peak voltage divided by the square root of 2, or 0.707 times the peak voltage. RMS stands for root mean squared. The RMS value is the square root of the mean, or average value, of the squared function of the instantaneous values. The term RMS is not used in DC circuit analysis or calculations where the magnitude is always constant. Most multimeters, either voltmeters or ammeters, measure RMS value, assuming a pure sinusoidal waveform. The RMS value of a sinusoidal waveform gives the same heating effect as a DC current of the same value. That is, if a direct current, I, passes through a resistance of R ohms, the DC power consumed by the resistor as heat is I squared R watts. If an alternating current, I equal to I max sine of theta, flows through the same resistance, the AC power converted into heat will be the I RMS value squared times R watts. When dealing with alternating voltages and currents, they should be treated as RMS values unless otherwise stated. Therefore, an alternating current of 10 amperes will have the same heating effect as a direct current of 10 amperes and a maximum value of 14.14 amperes. Lastly, again, I show a sine wave in the dark blue curve, and I show the maximum value, the RMS value, the average value, and the function, a function of time, is the maximum value times sine omega t, where omega is in radians per second, t is in time, So omega t is in radians or theta, and the sine wave varies from 0 to pi radians to 2 pi radians. And here I summarize that the RMS value is equal to 0.707 of the peak value, or 0.3536 of the peak-to-peak value, or 1.11 of the average value. Why is the sine wave important? An AC generator uses the principle of Faraday's electromagnetic induction to convert mechanical energy to electrical energy. A sinusoidal waveform results. A simple generator consists of a pair of permanent magnets producing a fixed magnetic field between a north and a south pole, as shown in the bottom right diagram. Inside this magnetic field is a single rectangular loop of wire that can be rotated around a fixed axis, allowing it to cut the magnetic flux at various angles. I've included at the bottom left a picture of a single coil DC motor. It consists of a battery, 2 paper clips, a neodymium boron magnet, and a rotor consisting of magnet wire wrapped in multiple loops with 2 ends sticking out that form the shaft of the rotor and is supported by the 2 paper clips. Here is the explanation of the single coil AC generator. As the coil rotates anti-clockwise around the central axis, which is perpendicular to the magnetic flux, the wire loop cuts the lines of magnetic flux set up between the north and south poles at different angles as the loop rotates. The amount of induced EMF in the loop at any instant of time is proportional to the angle of rotation of the wire loop. As this wire loop rotates, electrons in the wire flow in one direction around the loop. When the wire loop has rotated past the 180-degree point and moves across the magnetic lines of flux in the opposite direction, the electrons in the wire loop flow in the opposite direction. The direction of the electron movement determines the polarity of the induced voltage. When the loop or coil physically rotates one complete revolution, or 360 degrees, one full sinusoidal waveform is produced, with one cycle of the waveform being produced for each revolution of the coil. As the coil rotates within the magnetic flux, the electrical connections are made to the coil by means of carbon brushes and slip rings, which are used to transfer the electrical current induced in the coil. The amount of EMF induced into a coil cutting the magnetic lines of flux is determined by the speed at which the coil rotates inside the magnetic flux, the strength of the magnetic flux, and the length of the coil or conductor passing through the magnetic flux. One cycle of induced EMF is produced each full revolution of the coil through a magnetic flux comprised of a north and south pole. If the coil rotates at a constant speed, a constant number of cycles will be produced per second, giving a constant frequency. By increasing the speed of rotation of the coil, the frequency is also increased. Therefore, frequency is proportional to the speed of rotation. Also, the simple single coil generator has just one pair of poles. Add more magnetic poles to the generator so that it has 4 poles. Then for each revolution of the coil, 2 cycles will be produced for the same rotational speed. Therefore, frequency is proportional to the number of pairs of magnetic poles. At the bottom left, we see a diagram that defines what a radian is. Here we have a circle of radius r, and the angle that gives a arc length equal to the radius is 57.3 degrees. We define that as 1 radian. Omega, frequency, has units of radians per second, and it's related to the frequency f, cycles per second, or hertz, by the equation omega equals 2 pi f. Here we see the induced voltage as the coil rotates through the magnetic flux. And we see the voltage is equal to V max sine omega t, where omega t is radians per second times second, or theta in radians. And we see the sine wave that is created by this voltage as the coil rotates through the magnetic flux. Here we see two diagrams that will show the equivalence of phase angle and time delay. At the top, we see two sine waves, one for voltage, one for current, that are in phase. At the bottom, we see two sine waves, one for voltage, one for current, and they are 30 degrees out of phase. The current leads the voltage by 30 degrees. This phase angle is equivalent to a time delay. According to the formula, phase angle divided by 360 degrees times the period of the sine wave will give us the time delay, where the period t is in seconds and is 1 over f, which is in hertz. So time delay and phase angle are equivalent. The diagrams at the top show what we mean by in phase, positive phase, and negative phase. At the bottom left, we see a sine and a cosine, and they're 90 degrees out of phase. At the bottom right, we see a voltage curve and a current curve, sine waves, and we see that they are 30 degrees out of phase. These are just examples of curves that are in phase or have leading or lagging phase angles. We will have the occasion to use complex numbers in our analysis. In the XY plane, here we see the positive real axis and the positive y-axis, which we now call the positive imaginary axis. We see that we can locate any point in this plane by two coordinates, a real coordinate and an imaginary coordinate. Hence, complex numbers are made up of a real component and an imaginary component, an x component and a y component. J represents the square root of y minus 1. It's the imaginary number. And we use polar coordinates to represent complex numbers and to analyze complex expressions. By that I mean this x plus jy complex number can be represented by its magnitude. According to our right triangle relationship, a is equal to the square root of x squared plus y squared. And the tangent of this angle theta is y over x, opposite over adjacent. Similarly, x is equal to a cosine theta, y is equal to a sine theta. Representing complex numbers using this polar representation, we can then take two complex numbers, here Z1 and Z2, with magnitudes A1 and A2 respectively, and angles theta1 and theta2 respectively. And when we multiply them together, we multiply the magnitudes and add the angles. If we divide one by the other, we divide the magnitudes and subtract the angles. So multiplication and division are made much simpler by using this polar representation. And since our use of complex numbers, complex expressions, will be through multiplication and division, this representation then is most useful. Let's now talk about two of the laws of nature that are used in analyzing electrical systems. They are Kirchhoff's voltage and current rules. I call them rules rather than laws because these rules are derivable from Maxwell's equations. So they are not independent laws, but are simply rules derivable from Maxwell's equations, which are the true laws of nature. Kirchhoff's voltage rule, or the loop rule, says the algebraic sum of the voltages around any closed circuit path is zero. Kirchhoff's current rule, or node rule, says the algebraic sum of currents flowing into or out of a junction is zero. Electrical elements are represented by their impedances, Z. Impedances in Z in series have the same current flowing through them, and the equivalent impedance is simply equal to the sum of the individual impedances in series. Impedances in parallel have the same voltage across them. The reciprocal of the equivalent impedance is equal to the sum of the reciprocals of the impedances in parallel. Here we see in diagram form Kirchhoff's current rule or current law, KCL, as it is usually called. And we see currents entering the node equals the currents leaving the node, Kirchhoff's current law. Here is KVL, Kirchhoff's voltage law or voltage rule. It says the sum of all the voltage drops around the loop is equal to zero. So the voltage drop from A to B, plus the voltage drop from B to C, plus the voltage drop from C to D, plus the voltage drop from D to A must equal zero. Here's a typical DC circuit. We have all resistances, but remember these resistances can be replaced by impedances of resistors, capacitors, or inductors. Here we see nodes, branches, and loops. Components are said to be connected in series if the same current flows through all the components. So resistors 5, 6, and 7 are in series because the same current flows through all of them. The equivalent impedance is the sum of those three resistances. Components are said to be connected in parallel if they have the same voltage applied across them. Here, if we replace resistors 5, 6, and 7 by their equivalent impedance, Z, which is the sum of the resistances, we see then that equivalent impedance is in parallel to resistor 4 as they have the same voltage across them, the voltage between this node and this node. These diagrams show two different approaches to solving circuit problems. One is called loop current analysis. Here we assign currents to loops I1, I2. So the current flowing through the 40 ohm resistor is equal to I1 minus I2. Using node voltage analysis, we assign currents to each element. I1 is the current through the 10 ohm resistor, I2 is the current through the 20 ohm resistor, I3 is the current through the 40 ohm resistor. So VA minus VB divided by the resistance R10 will give me the current flowing through this resistor, I1. Here we have an example problem. The problem shows two voltage sources, E1, a function of time, E2, a function of time. And while we have not talked about inductances or capacitances, I include an inductor and a capacitor in this example. Here we show an inductor L in parallel with the resistance R1. We have resistor R3 and resistor R2. And we have capacitor C. R2 and C are in parallel as L and R1 are in parallel. The impedance of a resistor is R, so the impedances of R1 is R1. The impedance of R2 is R2. The impedance of R3 is R3. We will learn that the impedance of the inductor is simply the inductance times D, which is a differential operator, which we just treat algebraically. The impedance of a capacitor is 1 over CD, again, where D is the differential operator, which we just treat using algebra. So if I now use those values for the inductances, or just leave the inductances in terms of Z, I have ZL and ZR1, ZR3, ZR2, and ZC. I note that ZL and ZR1 are in parallel. The parallel combination I define as Z1. I note that R2 and C are in parallel, so that parallel combination of impedances I call Z2. I then redraw my circuit, and I show my Z1 and Z2, which are the equivalent impedances for the two parallel combinations. I apply Kirchhoff's current law at node A, and then the rest is algebra, and I'll let you go through the details of the algebraic manipulation. We're looking ahead now and showing the use of this differential operator, which will transform derivatives and integrals into algebraic expressions. So d times a variable, it says take the derivative of that variable. As we will see, 1 over d times a variable says take the integral of that variable. This allows us to use the axioms, the rules of algebra, rather than dealing with differential equations, derivatives, and integrals to develop the equations of motion for our dynamic systems. So this is a preview of what is to come, and we will refer back to this in the future. As examples of the application of Kirchhoff's voltage law and Kirchhoff's current law, I have worked 4 example problems. In problem 2 of these examples, I apply a principle called the superposition principle, which is applicable to linear systems. In this problem, there is a current source and a voltage source. The system is a linear one, so superposition applies. Superposition says that the output due to several inputs applied simultaneously is equal to the sum of the outputs with each input applied separately. And superposition applies here. So in this example, I apply the voltage source and replace the current source with an open circuit, and I find the output. Then I apply the current source, replace the voltage source with a short circuit, and find the output. The total output with both sources applied will be equal to the sum of the two outputs, a classical application of the superposition principle. In problem number 4, I show two methods of analysis. The first method assigns separate currents to each resistor. The second method, the loop current method, applies a current to each loop. I'll allow you time to go through these KVL and KCL example problems. Here are problems 1 and 2. And here are problems 3 and 4. Here we see two very useful formula. One is called the ideal voltage divider. It relates two resistors in series, or two impedances in series, to the voltage in and the voltage at the node between the two resistors. And this assumes that there is no current being drawn from this circuit. I out is 0, meaning that the circuit is not being loaded by anything connected to it. And what it says is that the output voltage, the voltage across resistor R2, is equal to the input voltage times the ratio of R2 to the sum of the two resistors, R1 plus R2. And the resistances can be replaced by impedances. The current divider, shown here, has an input current IN, which then splits. Part goes through R1, part goes through R2. The currents come together, and I out equals I in. Using KVL and KCL, in both the voltage divider and current divider, will result in our application rules. Here, the rule for I1 is that I1 equals I in times R2 over the sum of R1 plus R2. And I2 is equal to R1 over the sum of R1 plus R2. And again, the resistances can be replaced by impedances. And these equations can be verified by simple application of Kirchhoff's voltage rule and Kirchhoff's current rule. We now turn to two very useful concepts in analyzing complex linear systems: the Thevenin equivalent circuit and the Norton equivalent circuit. In each case, the starting point is a linear network consisting of several energy sources and impedances. It does not have to be resistances. It can be impedances of resistors, capacitors, inductors in any combination, as long as the combination is a linear one. The Thevenin theorem and Norton theorem are analytical methods used to change a complex circuit into simple equivalent circuits consisting of a single resistance in series with a voltage source, as we see here for the Thevenin equivalent circuit. RL is the load resistance. We've transformed this linear network into a voltage source and a series resistance. And for the Norton equivalent circuit, we transform this complex network into a current source in parallel with a single resistance or single impedance. And RL again is the load resistance. These two concepts are very, very useful in reducing complex linear networks into very simple systems so as to determine the effect of adding a load to the complex circuit. Let's talk more formally about Norton and Thevenin equivalent circuits. Thevenin's theorem says that any circuit network of linear elements can be replaced by an equivalent circuit consisting merely of a single voltage source, V sub Thevenin, TH, and a single series resistance, R Thevenin, or single series impedance. And this is the exact representation of a simple real voltage source, as we will see. Simplifying a complex circuit will simplify the analysis of it. So to calculate the values of V Thevenin and R Thevenin, we follow three simple steps. The first step is to find the open circuit, that is the no current flow, output voltage, V open circuit, across the output terminals without the load being added to the output. So this is V open circuit of the actual circuit. Next, in the actual circuit, we replace any voltage sources with a short circuit, that is an ideal wire with no resistance, and any current sources with an open circuit, that is no connection, infinite resistance. We redraw the circuit and determine the total resistance, or total, now appearing across the output terminals. Then V open circuit is V Thevenin, and R total is R Thevenin. And again, note that we can replace the word resistance with the word impedance, and the concept is still valid. So we see here the Thevenin equivalent circuit consists of a voltage source, V Thevenin, in series with a Thevenin resistance, R Thevenin, and we attach our load to the output. And this then replaces the complex linear network. Norton's theorem is a theorem that is less often used, but complements Thevenin's equivalent circuit theorem. Norton's theorem says that any complex circuit of linear elements can be simply represented by a single current source, I Norton, and a single parallel resistance, R Norton. And to calculate the values of I Norton and R Norton, we follow three simple steps. First, determine the current that would flow through a short circuit connected across the output terminals. This is the short circuit current flow, I sub SC, short circuit. Then in the actual circuit, replace any voltage sources with a short circuit and any current sources with an open circuit. Redraw the circuit and determine the total resistance, or total, now appearing across the output terminals. This is identical to step 2 for the Thevenin equivalent circuit. Then I short circuit equals I Norton, and R total equals R Norton. And again, note that we can replace the word resistance with impedance, and the concept is still valid. So the Norton equivalent circuit consists of a Norton current source, I Norton, and a parallel resistance, the Norton resistance, R Norton. And to this equivalent circuit, we connect our load. What is the relationship between the Thevenin equivalent circuit and the Norton equivalent circuit? A circuit can be simplified by finding either the Thevenin or the Norton equivalents. Which equivalent you choose is dependent only on whether you want the original circuit to act as a voltage source or a current source. The Thevenin and Norton resistances of a circuit are equal. R Thevenin equals R Norton. The voltage developed across the Norton resistance by the Norton current is equal to the Thevenin voltage. That is R Norton times I Norton equals V Thevenin. Since R Norton equals R Thevenin, we also see that I Norton equals V Thevenin divided by R Thevenin. So if one of the equivalent circuits has been determined, it is an easy job to find the other. I've included here now 4 pages of very simple examples to show the importance of the Thevenin equivalent circuit and the Norton equivalent circuit, and also the relationship between the two. So please work through the problems I have here on this slide, and then the next slide, the third slide, and lastly, the fourth slide, which shows the relationship between the Norton equivalent circuit and the Thevenin equivalent circuit. And again, these concepts are very important for simplifying complex linear networks into a simple voltage source and a series resistance, or a current source and a parallel resistance, to which we can then add our load and determine the performance of the loaded circuit. Impedance matching. The major factor in understanding impedance matching stems from the realization that the output of almost any circuit can be represented as either a Thevenin equivalent circuit or a Norton equivalent circuit, where the associated internal impedance is more commonly called the output or source impedance. The load circuit connected to the output of almost any circuit can be represented by a single impedance and is usually called either the load or input impedance. Impedance matching simply means finding the best values for the output impedance of the source and the input impedance of the load to satisfy certain conditions. Impedance matching for voltage transfer. Voltage transfer means transferring a voltage from a source circuit to a load circuit. We usually want as much voltage as possible to be transferred, and when this has been achieved, we say that we have good voltage transfer. The condition for good voltage transfer is met if the source resistance is much less than the load resistance, or equivalently, the source impedance is much less than the load impedance. We have acceptable voltage transfer if the load resistance is at least 10 times larger than the source resistance. Impedance matching for current transfer. There are times when we are interested in transferring current rather than voltage. These are when we have a current source or a circuit which can be represented as a current source, which has a load circuit requiring as much current as possible from the source. Current transfer means transferring a current from a source circuit to a load circuit. We usually want as much current as possible to be transferred. When this has been achieved, we say that we have good current transfer. The condition for good current transfer is met if the load resistance is much, much less than the source resistance, or if the load impedance is much, much less than the source impedance. We have acceptable current transfer if the load resistance is at least 10 times smaller than the source resistance. Lastly, impedance matching for power transfer, which is probably the most important of the three. Impedance matching for power transfer may be the most important condition for applications involving output to the real world. It tackles the problem of transferring power from one circuit to another. For maximum power transfer to occur, we need the source resistance to equal the load resistance, or equivalently, the source impedance to equal the load impedance. This outcome is not obvious, but it can be deduced intuitively by considering that for maximum output voltage, we want the source resistance to be much, much less than the load resistance. And for maximum output current, we want the source resistance to be much, much larger than the load resistance. But because power is voltage times current, we require a condition which satisfies both inequalities. So it is not surprising that for maximum power transfer, the source resistance should equal the load resistance. Mathematically, we can derive this as follows. Using our voltage divider, we can see that the load voltage is equal to the load resistance divided by the sum of the load resistance and the source resistance times the voltage source. Power for the load is equal to the voltage across the load squared divided by the load resistance. And it equals this expression just from substitution. Mathematically, we know we have a maximum if I take the derivative of this power with respect to the load resistance and set it equal to 0. If I then solve for the load resistance, I see that the load resistance will equal the source resistance to make this equation equal to 0. And this will maximize power transmission. I can show this result by this simple example. Here I have a source voltage, a series resistance, and then a load resistance in series with the source resistance. If I let the source resistance be 25 ohms and fixed, and the voltage source be 100 volts and fixed, but I vary the load resistance between 0 and 100 ohms, I'd like to find out the relationship between RS and RL to allow for maximum power transfer. The current flows through RS and RL is the same as they are both in series, have the same current flowing through them, and the source voltage is dropped across the sum of RS and RL. So the current in the circuit is given by Vs, the source voltage, divided by the sum of RS and RL. Power delivered to the load is I squared RL. If I now plot power versus load resistance, the graph shows me that I get a maximum value of power when the load resistance equals 25 ohms, which is the same as the source resistance. So this verifies our mathematical result. Electrical sources. There are two types of electrical sources, voltage source and a current source. An electrical source is a device that supplies electrical power to a circuit. Both types of sources can be classified as a direct current, DC, source, or as an alternating current, AC, source. Electrical sources supply energy, and they can convert non-electrical energy into electrical energy, and vice versa. For example, a battery converts chemical energy into electrical energy, while an electrical machine, such as a DC generator, converts mechanical energy into electrical energy. Renewable technologies can convert energy from the sun, the wind, and waves into electrical or thermal energy. As well as converting energy from one source to another, electrical sources can both deliver and absorb energy, allowing energy to flow in both directions. An important characteristic of an electrical source, and one which defines its operation, is its current voltage characteristic curve. Here we see an ideal constant voltage source. This voltage source will supply whatever current is required by the circuit connected to it. Here we see an ideal alternating voltage source, and the alternating voltage source will supply whatever current the circuit connected to it requires. Here we see an ideal constant current source, and this constant current source will supply a constant current regardless of the voltage required by the circuit connected to it. So these are all ideal voltage and current sources, and again, will supply whatever is needed by the circuit with no limitations. Let's first talk about voltage sources. An ideal voltage source is defined as a two-terminal active element that is capable of supplying and maintaining the same voltage across its terminals, regardless of the current flowing through it. An ideal voltage source is known as an independent voltage source, and its voltage does not depend on either the value of the current flowing through the source or its direction, but is determined solely by the value of the source alone. For example, an automobile battery has a 12-volt terminal voltage that remains constant if the current through it does not become too high, delivering power to the car in one direction and absorbing power in the other direction as it charges. A dependent voltage source, or controlled voltage source, provides a voltage supply whose magnitude depends on either the voltage across or current flowing through some other circuit element, which can be either time varying or constant. Here we see diagrams of ideal and real voltage sources. Here are the ideal voltage sources. A diagram for a general one, for a battery, and for a generator. And we note that the voltage is constant, whether it's delivering power or absorbing power, regardless of the current flowing. Here is a schematic of an ideal voltage source, and we note that the output impedance or output resistance is 0. The output voltage is the same as the supply voltage. A practical voltage source or a real voltage source has an output resistance, an output impedance. And so as this diagram shows, as the current increases, the output voltage will drop because of this output impedance or output resistance. A real voltage source. An ideal voltage source can provide a voltage supply that is independent of the current flowing through it. That is, it maintains the same voltage value always. An ideal voltage source has zero internal resistance. In the real world, the terminal voltage will decrease with an increase in load current. All voltage sources have a small internal resistance, which reduces their terminal voltage as they supply load currents. For non-ideal or practical voltage sources, such as batteries, the internal resistance produces the same effect as a resistance connected in series with an ideal voltage source, as these two series-connected elements carry the same current. Voltage sources can be connected in both parallel or series, as for any circuit element. Series voltages add together, while parallel voltages have the same value. Note that unequal voltage sources cannot be connected directly together in parallel. A real voltage source resembles a Thevenin equivalent circuit, as Thevenin's theorem states that any linear network containing impedances and sources of voltage and current may be replaced by a single voltage source in series with a single impedance. If the series source resistance is low, the voltage source is ideal. When the source resistance is infinite, the voltage source is open-circuited. In a real voltage source, the decrease in the angle of the slope of the current voltage characteristic curve as the current increases is known as regulation. And we see that here in the graph, the decrease in the voltage output as the current increases. Voltage regulation is an important measure of the quality of a real voltage source, as it measures the variation in terminal voltage between no load, when the load current is zero, that is open circuit, and full load, when the load current is maximum, that is a short circuit. As a battery example, a battery supply consists of an ideal voltage source in series with an internal resistor. And we see that in this diagram here. An ideal voltage source in series with an internal resistor, here represented as 2 ohms. The voltage and current measured at the terminals of the battery were found to be Vout1 equals 130 volts at 10 amps, and Vout2 equals 100 volts at 25 amps. So here we have 130 volts at 10 amps and 100 volts at 25 amps. And we're asked to calculate the voltage rating of the ideal voltage source and the value of its internal resistance. We draw the current voltage characteristic curve, and indeed we see that the slope of this curve is 2 ohms, which is the output impedance or internal resistance of this battery. A controlled voltage source changes its terminal voltage depending upon the voltage across or the current through some other element connected to the circuit. Dependent voltage sources can be controlled by an input voltage, a voltage-controlled voltage source that we see here. A voltage-controlled voltage source is controlled by some voltage Vin, and the output, the dependent voltage, Vout, is proportional to Vin, the controlling voltage, through the scaling factor mu. Here we have a controlling current, and here the dependent voltage output is proportional to the controlling current, with the scaling factor designated by the symbol ρ. This is a current-controlled voltage source. Current source. An ideal current source is a circuit element that maintains a constant current flow regardless of the voltage developed across its terminals. It continually provides a specified amount of current regardless of the impedance that it is driving. As with voltage sources, the current source can be either independent, ideal or real, or dependent, controlled by a voltage or current elsewhere in the circuit, which itself can be constant or time varying. It may be difficult to specify the magnitude and polarity of the voltage of an ideal current source as a function of the current. We may know the current supplied by the current source, but not the voltage across it, unless the power supplied by the current source is given, as power equals voltage times current. However, if there is more than one source, then the terminal voltage will be dependent upon the network in which the source is connected. Here are pictures of ideal current sources. The general ideal current source, a generator, and the ideal current source either delivers power and absorbs power with a constant current regardless of the output voltage. So here is our ideal current source. Here we see the ideal current source with no internal resistance, no internal impedance. All of the current flows out of the source into the circuit connected to it. However, a practical current source or real current source has an input resistance in parallel with the ideal current source. This internal resistance or impedance causes some of the current to be diverted from going to the output circuit. So we see here that the current from the ideal source, some of it goes through this internal resistance and the rest will go out to the circuit connected to the source. And we see that the amount of current that gets diverted is equal to V out over R sub P. And the slope of this line is minus R sub P, which is this internal resistance. Connecting two or more current sources in parallel is equivalent to one current source whose total current output is given as the algebraic addition of the individual source currents. Current sources of different values may be connected in parallel. Current sources are not allowed to be connected in series, either of the same value or ones with different values. An ideal current source can supply the same amount of current indefinitely regardless of the voltage across its terminals. This implies that the current source has an infinite internal resistance. Real-world current sources always have an internal resistance, causing the generated source to vary with load. A real current source can be represented as an ideal source with an internal resistance connected across it. The internal resistance produces the same effect as a resistance connected in parallel with the current source. A real current source resembles a Norton equivalent circuit, as Norton's theorem states that any linear network containing impedances and sources of voltage and current can be replaced by an equivalent circuit consisting of a constant current source in parallel with a resistor. If this parallel resistance is very low, the current source is short-circuited. If the parallel resistance is very high or infinite, the current source is modeled as ideal. An ideal current source plots a horizontal line on the current voltage characteristic curve. as real current sources have an internal source resistance, which takes some of the current. The characteristic curve is not flat and horizontal, as the current is now splitting into two parts, with one part flowing into the parallel resistance and the other part flowing straight to the output terminals. The voltage drop across the resistance is equal to V out with no load attached. For an ideal current source, the resistance is infinite, as there is no internal resistance. The terminal voltage is zero, as there is no voltage drop. Kirchhoff's current law tells us that I out equals I source minus V out over R sub P, the internal resistance. This equation is plotted here to give the current voltage characteristic curve of the output current. It is a straight line with slope minus RP, which intersects the vertical voltage axis at the same point as IS when the source is ideal. An ideal current source provides a specified amount of current completely independent of the voltage across it, and as such will produce whatever voltage is necessary to maintain the required current. This then makes it completely independent of the circuit to which it is connected to, resulting in it being called an ideal independent current source. A controlled or dependent current source changes its available current depending upon the voltage across or the current through some other element connected to the circuit. In other words, the output of a dependent current source is controlled by another voltage or current. An ideal dependent voltage controlled current source maintains an output current I out that is proportional to the controlling input voltage, V in. And we see that here. A voltage controlled current source is controlled by V in with the scaling factor given as alpha. The output current is defined by the equation I out equals alpha times V in. The multiplying constant alpha has the unit amperes per volt. An ideal dependent current controlled current source, which we see here, maintains an output current that is proportional to a controlling input current. As the controlling current I in determines the magnitude of the output current I out times the magnification constant beta. I out equals beta times I, the current supplied by the ideal current source. The output current is determined by the equation I out equals beta times I in. The multiplying constant beta has the unit amperes per ampere. It is dimensionless. Let's extend our discussion to include now current and voltage meters, along with current and voltage sources. So we'll combine the two together and we'll see the similarities among them. So we know that an ideal voltage source supplies the intended voltage to the circuit no matter how much current and thus power this might require. It can supply infinite current. It has zero output impedance, which means its internal resistance is zero. We also know that an ideal current source supplies the intended current to the circuit no matter how much voltage and thus power this might require. It can supply infinite voltage. It has infinite output impedance. That means its internal resistance is infinite. Real sources have terminal characteristics that are somewhat different from the ideal cases, as we have learned. However, the terminal characteristics of the real sources can be modeled using ideal sources with their associated input and output resistances, as we have also learned. So to review, a real voltage source is modeled as an ideal voltage source in series with a resistance called the output impedance of the device. When a load is attached to the source and current flows, the output voltage Vout will be different from the ideal voltage source Vs due to voltage division. The output impedance, that is the internal resistance, of most voltage sources is usually very small, a fraction of an ohm. For most applications, the output impedance is small enough to be neglected. However, the output impedance can be important when driving a circuit with small resistance because the impedance adds to the resistance of the circuit. A real current source can be modeled as an ideal current source in parallel with an output impedance. When a load is attached to the source current, Is, divides between the output impedance and the load. The output impedance, that is the internal resistance, of most current sources is usually very large, minimizing the current division effect. However, the impedance can be important when driving a circuit with a large resistance. And here we see two diagrams. A real voltage source consists of an ideal voltage source and an output impedance in series. A real current source consists of an ideal current source with an output impedance in parallel. Let's turn our attention to meters. An ideal voltmeter has infinite input impedance. It draws no current. A real voltmeter can be modeled as an ideal voltmeter in parallel with an input impedance. The input impedance is usually very large, 1 to 10 mega ohms. However, this resistance must be considered when making a voltage measurement across a circuit branch with large resistance, since the parallel combination of the meter input impedance and the circuit branch would result in significant error in the measured value. An ideal ammeter has zero input impedance, no voltage drop across it. A real ammeter can be modeled as an ideal ammeter in series with a resistance called the input impedance of the device. The input impedance is usually very small, minimizing the voltage drop V sub R added in the circuit. However, this resistance can be important when making a current measurement through a circuit branch with small resistance, because the output impedance adds to the resistance of the branch. Here we see a picture of a real voltmeter, which consists of an ideal voltmeter and an input impedance, Rin. Here we see a real ammeter, which consists of an ideal ammeter and an input impedance, Rin. Here we see a real voltage divider that has a real voltage source and a real voltmeter. The real voltage source consists of an ideal voltage source and an output impedance. The real voltmeter consists of an ideal voltmeter and an input impedance. For an ideal voltage divider that has an ideal voltage source and an ideal voltmeter, R out for the voltage source is 0, R in for the ideal voltmeter is infinite, and so we know that the measured voltage then is the source voltage times our voltage divider ratio, R2 over R1 plus R2. However, for a real voltmeter, for example, a multimeter has an input impedance of 10 mega ohms, while an oscilloscope has an input impedance of 1 mega ohm. And a real voltage source, for example, a waveform generator, has an output impedance of 50 ohms. If we conclude these values in our analysis, we see that R out for the voltage source is in series with R1, and R2 is in parallel with R in for the real voltmeter. So if we include that in our analysis, then the real voltage divider is given by this expression here. And we note that if R1 is much, much greater than R out, R1 much, much greater than R out, and R2 much, much less than R in, then this expression for the real voltage divider will reduce to the ideal expression for the voltage divider. Let's talk about circuit loading. Here I show an ideal voltage source connected to a voltage divider, where normally we assume that the output current is zero. However, that is not a complete description of this voltage divider circuit. In order to completely describe a circuit, we must know the voltage and current at both the input and output ports. We must know power in and power out. So in order to get that complete description, we apply Kirchhoff's current law, where to this node where we see that I in equals I out plus the current going through the R2 resistor. Ohm's law says for the R2 resistor that current through R2 equals E out over R2. And Kirchhoff's voltage law around the closed circuit says that E in minus I in, which is the same as IR1, times R1 is the voltage drop across R1, minus E out, which is the voltage drop across R2, must equal zero, Kirchhoff's voltage law. If I now take these equations and I arrange them in what we call a matrix representation, which is just algebra and just a convenient way to represent these equations. So if you're familiar with matrices, and you will become familiar with matrices, as MATLAB stands for Matrix Laboratory, and we will be using MATLAB extensively, you can read this as E out equals 1 times E in minus R1 times I in. I out equals minus 1 over R2 times E in plus R2 plus R1 over R2 times I in. And these are then the equations that we see here on the left, applying Kirchhoff's current law and Kirchhoff's voltage law. So the complete description is then given by this matrix representation. Now, this should collapse to the unloaded equation for an ideal voltage divider if I just make I out equal to zero. If I do that, then this matrix formulation, which is a complete system description, reduces to these two equations. And if I simplify the mathematics using algebra, I get that E out equals E in times R2 over R1 plus R2, which is my ideal voltage divider equation, assuming that I out equals zero. So whenever we use this ideal voltage divider equation, we are assuming implicitly, or we must guarantee, that I out equals zero. Here we show again an ideal voltage source to a voltage divider with a real voltmeter consisting of an ideal voltmeter through which no current will flow and its input impedance shown as R in. So here I out does not equal 0 as it goes, some of it, I out goes through R in. So R2 and R in are in parallel, and R1 then forms a voltage divider with a parallel combination of R2 and R in, as I say here. If I apply that, I get my equation then for E out as E in multiplied by this ratio. If I note that R2 is much, much smaller than R in, then that then essentially tells me that there is no loading and I out is essentially 0. Then I get my ideal voltage divider equation. R in is usually very large. For an oscilloscope, it's approximately 1 mega ohm, and for a multimeter, it's 10 mega ohms. But if R2 is in the same order of magnitude, then you cannot make the assumption that I out is equal to 0, and this equation then needs to be used. So here then is our general loading case shown as two subsystems. On the left, we see our ideal voltage source with our voltage divider. And at the output terminal, we have output voltage and output current. Then we have our real voltmeter, which has an input current and an input voltage, and the output current into the ideal voltmeter is equal to 0. So when I connect the voltmeter to this voltage divider, E out is the same as E in, I out is the same as I in. And rather than having to then connect these two circuits and do an analysis of the combined circuit, I can use the matrix representations for each. Here is the matrix representation for the ideal voltage source and the voltage divider. Here is the matrix representation for the real voltmeter. And I can simply then equate E out to E in and I out to I in. E out to E in, I out to I in. If I then proceed to perform matrix algebra, and if you're familiar with that, you can follow these details. If not, we will be using this extensively throughout the course. So you can solve for I in the second equation and substitute back into the first equation. So it requires some substitution, solving, substitution. And again, some more algebra. But in the end, we get our equation for E out equal to E in times this ratio, which is the same ratio we obtained when we considered the entire coupled circuit. Ideal voltage supply, voltage divider, real voltmeter. Now, the downstream circuit will always load the upstream circuit. The question always is, how much? And then what to do. Ignore it at your own peril. Don't ignore it. Know that it is present and model its effect. Adjust parameters accordingly to reduce the effect. Or you can prevent the loading by inserting a buffer op-amp in the unity gain voltage follower configuration between the circuits as shown. Here is an op amp in the unity gain voltage follower configuration, which we will cover in detail in the op amps portion of this course. The voltage divider upstream circuit now behaves in an unloaded way, and the load will see the full voltage. The reason is that the buffer op amp has infinite input impedance and zero output impedance in the ideal situation. And the ideal situation is very, very close to the real situation for the buffer op amp used within its capabilities. Here we see a diagram of the op amp, in this case the 741 op amp, wired in the unity gain voltage follower configuration. Here we see the circuit representation where we have 8 pins. Pins 1, 5, and 8 are not connected. Pin 2 is called the inverting input, which is connected to the output, hence we have negative feedback. Pin 3 is the non-inverting input, and that's where our input voltage gets connected. Pins 4 and 7 are our minus and plus power supply voltages, normally plus and minus 15 volts. And pin 6 is our output voltage. And again, for this device, ideally, this has an infinite input impedance and zero output impedance. Electrical impedance. We've talked about this throughout our discussion up until now. Let's formally talk about electrical impedance. A variable that flows through an element is impeded by the element. Electrical impedance is a generalization of the simple voltage over current relation called resistance for resistors. That's Ohm's law. It can be applied to capacitors, inductors, and to entire circuits. It assumes ideal linear behavior of the device. Electrical impedance is defined as the transfer function, a term you'll become familiar with. It's just the ratio, the algebraic ratio of an output over an input. The transfer function relating voltage to current is given here. And it's given as a function of D, which we've said is an algebraic term. It's the differential operator, but we treat it just as we do any variable in algebra. So there are no derivatives or integrals or differential equations. So the impedance is voltage over current, and for a resistor, it's a constant, resistance R. However, for an inductor and capacitor, we will see it is a function of this differential operator. So here are the impedances for pure, and by pure we mean only has the attribute for which it is named, ideal, meaning linear electrical elements. The constitutive equation for a resistor is given to us by Ohm's law. The voltage across the resistor is equal to the current through the resistor times the resistance. For a capacitor, the constitutive equation says the current flowing through the capacitor, and we know there is no current flowing through a capacitor, it's the current flowing in the circuitry around the capacitor, is equal to the capacitance times the time rate of change of the voltage across the capacitor. For an inductor, the constitutive equation is the voltage across the inductor equals the value of the inductance times the time rate of change of the current flowing through the inductor. If we just apply the differential operator, we see that this derivative of voltage across the capacitor can simply be represented by a capital D times that voltage. And the rate of change of the current through an inductor can be represented by simply a capital D times that current through the inductor. And so we see here the mathematical representation of the impedance of a resistor, capacitor, and inductor, noting that impedance is just voltage over current. And here we see it in diagram form. And impedance is most useful in characterizing the dynamic behavior of components and systems, as we will see throughout the entire course. If we consider analogies, which are very, very powerful in explaining to fellow engineers areas of engineering which they may not be familiar with, we can use the mechanical electrical analogy to understand better impedance. So again, the impedances for pure and ideal electrical elements is shown here. For a resistor, it's R. For a capacitor, it's 1 over C times the differential operator. And for an inductor, it's L times the differential operator. When we talk about frequency response, we simply let the differential operator equal I, the imaginary number, square root of -1, times omega, frequency in radians per second. Similarly, impedances for pure and ideal mechanical elements, as we will learn. A resistor is equivalent to a damper in that all energy is dissipated. And impedance for a mechanical system is force divided by velocity, while impedance for an electrical system is voltage divided by current. So here, just as for a resistor, the impedance of a viscous damper is independent of the differential operator. It's a constant B, the viscous damping coefficient. A spring has an impedance, force over velocity, of 1 over C sub S, which is the capacitance of the spring, times the differential operator. And for a mass, force over velocity is equal to the mass times the differential operator. Again, substituting in for D, the value of I times omega will allow us to then calculate the frequency response of our elements and our systems consisting of interconnection of all of these electromechanical elements. More on this as we proceed through the course, but this will give you a preview. Here we see the impedances of mechanical and electrical elements, and we see the graphs. So here, these are what we call frequency response plots. For a resistor, we see the magnitude is constant and the phase angle is 0. For a capacitor, we see that the impedance decreases nonlinearly with frequency and the phase angle is -90 degrees. For an inductor, we see that the impedance increases linearly with frequency and the phase angle is +90 degrees. For mechanical elements, where impedance is now force over velocity, for a damper, the impedance is a constant B with 0 phase angle. For a spring, a compliant element, we see that the impedance decreases nonlinearly with frequency. The equation is 1 over omega C sub S. The phase angle is -90 degrees. And for a mass, we see that the impedance is linear with frequency, as given by this line and this equation, and the phase angle is +90 degrees. So here we see the analogy between the electrical elements and the mechanical elements. Impedance for an electrical element is voltage over current. Impedance for a mechanical element is force over velocity. A damper is the same as a resistor. A spring acts like a capacitor. The mass acts like an inductor for this set of analogies. When we look at the impedances of electrical and mechanical elements and look at the frequency response, that is by substituting in I or J, which is the imaginary number, times omega for the differential operator, we see that we get an amplitude ratio and a phase angle. So a magnitude and a phase angle. The real portion of the magnitude is called the resistive part, the resistive impedance, as it has to do with resistance. And the imaginary part has to do with either the capacitance or inductance. And we call that the reactive impedance. So depending on whether this is positive or negative in magnitude, will determine whether this reactive impedance is due to either capacitance or inductance. So if Zx is a positive number, the reactance impedance is behaving like an inductor, and it's called inductive reactance. If it's negative, it's called capacitive reactance. We will cover this in great detail when we discuss capacitors and inductors and their reactance. So given R and X, one can always compute the magnitude and phase angle of the impedance using our formulas here, which you are familiar with. Since the sinusoidal impedance, which is what we call the frequency response, gives the amplitude ratio and phase angle of voltage with respect to current, if the impedance of any circuit, no matter how complex, is known from either theory or measurement, and either voltage or current is given, we can quickly calculate the other. The rules, as we know, for combining series or parallel impedances are simple extensions to the dynamic case of the rules governing series and parallel static resistance elements. If the same flow passes through two or more impedances, those impedances are said to be in series, and they are equivalent to a single impedance whose impedance is the sum of the individual impedances. If the same effort difference exists across two or more impedances, those impedances are said to be in parallel, and they are equivalent to a single impedance whose reciprocal is equal to the sum of the reciprocals of the individual impedances. So here is a diagram summarizing what we have just talked about. I'm using D as my differential operator, and to get frequency response, I let D equal J omega, where J is the imaginary number. And sometimes we use I, but I we don't want to confuse with current. For a resistor, the magnitude is constant, it's R, the phase angle is 0 degrees. For a capacitor, the magnitude is 1 over omega C. We see the magnitude decreases nonlinearly with frequency. The phase angle is constant at minus 90 degrees. For an inductor, we see the magnitude increases linearly with frequency. The phase angle is constant at plus 90 degrees. And here we see the mathematical expressions for impedance of the resistor, the capacitor, and the inductor. So all of our manipulations, whether it's looking at transient response or frequency response of all dynamic elements, will be through the use of the axioms of algebra and also trigonometry, but not taking derivatives and integrals or evaluating solutions of differential equations. So by using this differential operator, we transform the differential equations, the derivatives and integrals to algebraic expressions. So it's algebra that we need to be proficient in. This concludes the presentation on DC circuit analysis. Thank you for your attention.